Hey everybody, welcome back to my channel. Today we will be making another supercell, but what makes today different is we have a pretty complicated structure, or what appears to be a pretty complicated structure. We will be making a supercell with vacuum in the C, as in cat, dimension with samarium cobalt. And this structure is pretty unique in that it doesn't have 90-degree angles between all of its unit cell axes. So without further ado, let's get started. I happen to have the unit cell for samarium oxide. I must have named this wrong. Let me rename it quickly. Be samarium cobalt. Okay, let's open that up. So here is the unit cell, and as you can see, between the, I think it is the A and B axis, we do not have 90-degree angles. And so this is tricky if you follow my other videos, because it's just not straightforward how you would cut off the periodicity atoms, well, the atoms which make certain periodicity dimensions, how you would cut them off here. And so what I mean is, in the previous videos, what we had to do was we had to save the lattice as an XYZ, and before we save it as an XYZ, we have to cut off all of the repeating atoms, because if you just take a unit cell and you save it as a VASP file, what happens is the computer automatically deletes repeating atoms. So if I were to save this structure we have right here on our screen as a VASP file, the Vesta would save it a file whose coordinates could be used directly in an electronic structure software package. Whereas if I were to save this unit cell as an XYZ file, we couldn't do that because it would save all of the atoms and it would not delete the repeating atoms. Like, for example, it would not delete these two atoms. And that's a problem because it does not obey periodic boundary conditions with respect to the atomic coordinates that you input into the electronic structure software package. Okay, so now we have to get this working. So how are we going to do this for this type of space group? We are going to first just orient the A axis directly at you. And in the other videos, I could do this just by pressing A, but here you can't do that. So what we have to do is orient A directly at us, and then we can see periodicity in the A dimension. So what I'm then going to do is I'm going to rotate the unit cell such that this was the face we were just looking at, and I'm going to delete these atoms. Then I'm going to go back. Okay, so we can see what we just did. Now I'm going to do the same in the B dimension, which is where we just were. And you can see we need to delete these atoms here. So we've destroyed periodicity in the A dimension, destroyed periodicity in the B dimension, but because we want to add vacuum in the C dimension, we are actually going to conserve periodicity in the C dimension, which actually means to break it because we save as an XYZ. So that's complicated. Because we broke periodicity in the A and B dimensions, we can save it as an XYZ, and therefore, in terms of how the XYZ would be put into the electronic structure software package, periodicity would be preserved. But because we preserve periodicity and save it as an XYZ, then we cannot put it in the electronic structure software package because periodicity would be broken. So it's exactly opposite. Okay, so what we can do now is we can actually just go ahead and save this file. So go to File, Export Data, save it as same thing _XYZ. So we're saving it as an XYZ. Save. Do not save hidden atoms. Okay, what I'm going to do is make an extra copy of the samarium cobalt file. So I will call it samarium cobalt. I will rename it. We will name it, nope, it's not there. And not oxygen. We will name it with vacuum. So just VASP. Copy it over with, what is it? F5. Okay, had to remember that for a second. Okay, so go to our XYZ file, copy the atoms. You can see we have 9 atoms. Excuse me, to get some water. Copy the atoms. go into the vacuum file and paste them. If you can see here, actually between the A and B axis, we do have this angle. If it was between the A and C, the number would be down here. So we have 2 samarium atoms and 1, 2, 3, 4, 5, 6, 7 cobalt. So let's just change these. 2 samarium, 7 cobalt. And so the first 2 will be samarium, these 7, the remaining 7 atoms will be cobalt. And then we are going to add 10 angstroms of vacuum in the C dimension. Save this. Go to Vesta, Control O for open. Open up that file, and there you go. There is your vacuum added to the samarium cobalt input structure. Now, if you wanted to make a supercell, you would then have had to have just originally expanded this 2 by 2 by 2, which that is. I have other videos to show you how to do that. So that's not what's tricky here. What's tricky here is how do you cut this? How do you disable the periodicity in the A and B dimensions when you have this unit cell that has an angle between 2 of the unit cell axes? And there's another way you could do this. You wouldn't get this exact structure, but you wouldn't have to, but you'd be able to cut the unit cell in the old fashion. So I will actually go through that quickly here. So I'm going to go back to this unit cell here. And what we're going to do is we're going to do a basis transform, and then we're going to cut the unit cell how we know how to do it. So we're basically going to craft a new unit cell that's exactly identical to this unit cell, but it's going to have 90-degree angles between all of its unit cell vectors. So let's go ahead and expand this to 4 by 4 by 4. So I'll press apply. And what I'm going to do with this new unit cell, obviously I don't like the fact that it has this sort of angle to it. So I'm going to sort of orient it such that I can define where my new unit cell will be cut. And in my old videos, I like literally get lattice planes out, and you know what, I'll actually do that here, but you can kind of see where it already is. So what I'm going to do here is orient this towards our screen, because I can't just press one of these A, B, C's to orient it. So if I go into lattice planes, I go to edit lattice planes. Let me move this over a little bit. If I were to just guess what these lattice planes are, it'd be pretty hard for me to figure out like what would be the lattice plane that is up and down like this. So if I actually want to figure out what that lattice plane is, I press this white arrow here, and then I can just draw my line right through these atoms. And now that they're highlighted, and then I press calculate the best plane for the selected atoms. And you can see here it's selected that it's the -2, 1, 0 plane. So what I'm going to do is move this over a little bit. Let's try 1. Okay, now we're going to go back to 0. So you can see that I have the line through the samarium atom, this pink atom. This is samarium. And then I'm going to draw one unit cell over. So I'll go new and go to -1. Oops, looks like I need to go to -2. Okay. Now I want to have periodicity be in this dimension, so going across the page. So let's take highlight this white arrow here, and let's just go straight across. I don't know what this lattice plane possibly could be, but let's click new, change the color to a little bit of a contrast. Let's go red and select the best plane. And this is the 0, 1, 0 plane, happens to be. So now let's go to new, and we actually want it to be all the way down here. So let's go to 0. Okay, didn't work. -3. Also didn't work. -1. This one is 2. Okay, so 3. Come back up here. Let's go to just 1. There it is. Okay, now select OK. The next step, what we have to do is cut around our lattice vectors So let's reposition this. Select the white arrow again. Okay, so we've cut around the red lattice planes. Let's cut around the green lattice planes. Oops, it looks like I made a small mistake. Let me actually, I'm pressing Control Z now. This actually would work what I'm doing, but it's not as straightforward. What I'd like to do is go back to Edit Data, Unit Cell. Oops, sorry, not Unit Cell, Edit Data, Lattice Planes. I want to make this the most straightforward. So what we're going to do is move over our green lattice planes to have it be here. So I'm going to make this -1, and this one will be now -3. Okay, much better. This is more intuitive to me. So now let's recut around our lattice planes that we just made. Okay, now what we're going to do is click this rotate around the y-axis arrow. And as you can see here, we need to still define periodicity in this dimension, which should be very straightforward where it is. Okay, so here we actually have our new unit cell. And what we're going to do now is rotate it like this. We are going to open up an Excel spreadsheet, and you can pause the video right now if you want and set this up. So assuming you've done that, now we have this O column, which stands for origin. So what we're going to do is define relative unit vectors here. So select this atom, which will be the origin of our new unit cell. Maybe this samarium atom. So its coordinates are 1, 1, 2. So 1, 1, 2. And let's do the new A dimension, or unit vector, which will be here. We have coordinates 1, 1, 1, 1, 1, 1. Now let's go, this will be our new B dimension, 2, 1, 2, 2, 1, 2. Okay, go back to Vesta, and let's do our C dimension, which is 2, 3, 2. 2, 3, 2. Now here we're going to set this equal to this coordinate minus $ this coordinate. Oops. Minus $. Oh, why is it not letting me? Okay, well, let's just go here and then select the $. That's strange. Okay. And so we fill in this table here. And these coordinates are now this is our transformation matrix that we need to apply to a new unit cell. So now let's go back to Vesta. Let's open the original VAST file we had. Let's go to Edit Data, Unit Cell, Transform. Now let's go back to Excel and see what our transform was. So it's -1, 1, 1, 2. So -1, 1, right? 1, 2. Select OK. Yes, yes, OK. Apply. There it is. There's our new unit cell. And now this unit cell is what you can do the old procedure for adding vacuum on. So let us now save this file, export data. We are going to actually export it as a VAST file. So we'll go samarium cobalt new .vasp. For some reason I have to type the .vasp. Save it as Cartesian coordinates. Exit out of it. Open it up again. Okay. Now let's do the standard procedure that I've done in other videos. We are going to slice periodicity. Oops. We're going to slice periodicity in the B. Preserve periodicity in the C. Slice it in the A. file, export data. Now we do it as an XYZ. Save it. Do not save hidden atoms. So what I'm going to do is copy over new VASP. I'm going to rename it as samarium cobalt new vac dot VASP. Copy it over. Now go to new XYZ. And now we have 14 atoms. 3 of them are samarium. Go to new vac. You can see here the unit cells, there are no angles existing between the unit cells, so they are all, I guess, orthogonal. Paste in the XYZ. So we had 14 atoms, 3 of them are samarium. So that's 3 samarium, 11 cobalt. And let's add 10 angstroms of vacuum to the C dimension. Now let us open samarium cobalt new vacuum. There you have it. So there's 2 ways you can add vacuum to this this like P6mm something structure, or something that does not originally have, if I go all the way back, something that does not originally have orthogonal unit cell vectors. You can do one or two things. You can do the procedure I showed in the very beginning, where you just rotate the unit cell and see the new, and you actually see the translational dimensions, and you basically do the procedure I outlined, save it as an XYZ, yeah, and then I forget off the top of my head, but whatever I had said before. Or you can take this unit cell and make it such that the unit cell axes are orthogonal, and then do the procedure. And just to show that these are equivalent, we should do some expansion. So let's expand this one 5 by 5. Okay, so here we're looking at it head on, and you can see we have samarium in the center with this what looks like an octahedral of or hexagon of cobalt. Let's go back to here where we have our original one, and let's also expand this 5 by 5. Okay, and so this is the cut version. This is the cut version of this. So let's go back to how we had originally cut it. I'm going to delete this top right here. How did I have it? Like this. Okay. So let's move this over. Let's take a snippet of this. Okay. So as you can see, that they are equivalent in this dimension. That's good. Okay, now let us rotate this to the side. And let's see here. So what I see is, I see a square of samarium, and I see this alternating pattern of 2 cobalt, entire layer of cobalt, 2 cobalt. Let's go here. We should see the same thing. I see, yep, square of samarium, 2 cobalt, entire layer of cobalt. And that's pretty much it. On top, what do we see? We see alternating rows of samarium and cobalt. Let's see if we see this here. So we started at this orientation, and we do see that. Actually, you can see we have samarium, samarium, cobalt. We would have a samarium here had we cut out, like okay, here, let me cut it. So if we cut it like this, and then we look down on here, what you see is, actually, I don't see it here. Well, in any case, it definitely is. It definitely is. Oh wait, yeah, we do. We see it alternating and then a row of samarium, and here we see it alternating and then a row of samarium. Okay, yeah. Whereas this angle, you have the two. It's alternating every other row of samarium. Here it is alternating every one. There's no samarium to cobalt samarium like there is in this dimension. Okay, so those are your two options if you don't have an if you have a unit cell that whose unit cell axes are not orthogonal, you can either just figure out which atoms need to be deleted and add your vacuum that way, or make the unit cell axis orthogonal through the procedure I showed you, where you expose internal planes as the new external planes, such that the intersection of the new external planes is 90 degrees, forms a 90-degree angle. Okay, thank you for your viewership. As we've done with other videos, if you have questions, comments, leave them in the comment section. I will try my best to address them. I do have some videos backlogged. I want to do some videos on adsorption energy on surfaces in quantum espresso. I'm thinking for those videos we could do maybe dipole correction in SCF calculations. Okay, so I think I have one more too I want to look at, but if you want me to look at something you're doing in research or something that you're interested in, I will definitely put it on my list and eventually get to it. Okay, take care. Thank you for watching.